Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 9. Gauss-Laguerre Method and Quadrature. The Gauss-Laguerre method is a form of Gaussian quadrature, which is used to approximate the value of the integral by selecting specific sample integration points or nodes and associated weights. The Gauss-Laguerre method is a powerful quadrature method that handles specifically type 1 improper integrals of the following form. The method is particularly useful in scenarios where such integrals arise, as it provides a more accurate approximation compared to simpler methods like the trapezoidal or Simpson's rule. The integral is expressed as a weighted sum, where n is the number of quadrature points, xi and wi are the abscisses and corresponding weights, referred to as Gauss-Laguerre quadrature, and Rn is the global error, which is defined as follows. Where the upper or lower error bounds for a GLN estimate can be determined from the absolute maximum and minimum values of two nth derivative of f on the semi-infinite domain. The Laguerre polynomials are defined as follows. Higher-order polynomials can be obtained from lower-order ones using the following recurrence relationship. The first derivative of an nth-order Laguerre polynomial satisfy the following recurrence relation. The method uses a set of abscisses and associated weights to estimate improper integrals over semi-infinite domain, i.e., type 1 integrals. The abscisses for an n-point Gauss-Laguerre quadrature are the zeros of the nth degree Laguerre polynomial, i.e., roots of ln x equals 0. The associated quadrature weights, based on the properties of these polynomials, are calculated from the following equation. Some integrals that are not in standard type 1 form can be converted to standard form. For example, the integrals of integrands without the exponential term are transformed to the standard form as follows. Where gx is defined as e to the x times fx. Then we may write the approximation as a weighted sum as shown below, where the weights in uppercase W are the modified weights. Some type 1 integrals on a semi-infinite interval with a lower bound starting at a are transformed to the standard form as follows. Where gx is defined as e to the x times fx plus a. Then we may write the approximation as a weighted sum, where the weights in uppercase W are the modified weights. To obtain the abscisses, we calculate the zeros of the nth degree Laguerre polynomial using the Newton-Raphson method. To start the iteration, provide the Newton-Raphson method with a smart initial guess, i.e., a guess very close to actual 0. For the ith root, and for n less than 4, an initial guess value in close proximity to the true 0 is calculated with the following asymptotic approximation. For n greater than or equal to 4, we calculate an initial guess value by extrapolation using 3 preceding zeros, i.e., abscisses. The current estimate is obtained from the following Newton-Raphson iteration equation. The advantages of the method are: high-order accuracy can be achieved using GLN approximation. They converge very quickly for relatively small n if the integrals are in standard improper type 1 forms. The disadvantages of the method are: the theoretical error estimation procedure is not an easy task. They are not suitable for discrete functions. They are very poor at integrating non-exponentially decreasing integrands. Highly accurate quadrature sets are required to compute integrals with high accuracy. Let us consider the following type 1 integral with a singularity at x equals 0. and investigate the convergence of this integral using the Gauss-Laguerre method for increasing values of n. The given integral is not in the standard form. However, we can put the integral into the standard form by employing the u equals 2x substitution as follows. Then the numerical estimates are found by the following weighted sum. Here we will show how to find the abscisses and weights for n equals 5. However, normally we read the quadrature sets from Table B2 of the Appendix B of the textbook or use a computer code that calculates the quadrature set. Applying a root-finding method, we obtain the zeros of this fifth-degree polynomial and place them in the table we construct. The weights uses the derivative of L5, so we find it as shown. Evaluating the expression for wi's for each root, we find the weights. Then, for each integration point, we evaluate the function and the product of the function with corresponding weight. The sum of the values in the last column gives the numerical estimate for the integral GL5. The computed numerical estimates and the true absolute error for various n values from 2 to 64 are tabulated here. Note that the estimates depict improvement for increasing n and tend to converge to the true solution. We observe that the results with at least 2 decimal place accuracy were achieved for n values of less than 10. For n equals 64, an error of the order of 10 to the minus 5 was obtained, which is extremely difficult to achieve with such a small number of panels by the trapezoidal or Simpson methods. With this note, we conclude this lecture. That is all for now. See you next time with another topic. Bye.